Welcome to lesson 8.13. In this video, we will be finding what's called arc length, which is really just the length of a smooth curve. Let's take a look at this example. Let's say we're trying to find the length of the curve from x equals 0 to x equals 6. One way that we could do this is by estimating using the straight line distance between those 2 points. That would look something like this. However, this is not super accurate. You can see that the distance of this line is really not close at all to the distance of the actual curve, or the length of the actual curve. So let's divide it into 2 segments instead. Let's go from 0 to 3, from x equals 0 to x equals 3, and from x equals 3 to x equals 6. This would be a more accurate approximation. What if we did this with 6 segments instead of just 2? At this point, the sum of the lengths of our little segments here would be pretty close to the actual length of the curve. So the arc length approximation becomes more accurate as the number of segments increases. And this concept is very similar to the limit definition of the derivative, which we covered in lesson 2.2, and the limit definition of a Riemann sum, which was covered in lesson 6.3. So again, we're seeing the limit is the fundamental thing that we are using to get all of our other calculus concepts. Now, I'm not going to go over the exact proof for how we can get the arc length formula using a curve like this right now, but I will go over it at the end of the video if you're interested. For now, what you need to know is that the arc length formula is that L, the length of the segment, is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx, where we were trying to find the arc length from x equals a to x equals b. Where this comes from is combining the distance formula, d equals the square root of delta x squared plus delta y squared, with the concept of integration and limits. Now the full proof, again, will be at the end of the video if you're interested, but you will not need to be able to prove the arc length formula or do anything like that on the AP exam. Let's take a look at a sample multiple choice question. What is the length of the curve f of x is equal to 4 cosine x from x equals 1 to x equals 5? Again, we see that this is our arc length formula right up here. The first thing I'm going to do is I'm going to find f prime of x because I do need to use f prime of x in my arc length formula. If f of x was equal to 4 cosine x, that means that f prime of x is going to be equal to 4 times the derivative of cosine x. Derivative of cosine x is equal to negative sine x. So f prime of x is really negative 4 times the sine of x. Now I can set up my arc length formula. L is equal to the integral from a to b, and in this case, a is equal to 1, b is equal to 5, of the square root of 1, that stays the same every time, plus f prime of x squared. Now f prime of x we already found is negative 4 times the sine of x, and then we're squaring that, and then we just stick our dx on the end. At this point, I would just get out the calculator and evaluate this integral. So we hit the math button and then number 9 to get it to an integral, and then we're going from 1 to 5, and then we are taking the square root of 1 plus, and then open parentheses here, negative 4 sine of x, and then make sure you square it on the outside of those parentheses, delta x at the end, dx. And we get 12.220, which matches answer choice D. What is the length of the curve f of y equals negative 3y cubed on the interval from negative 1 is less than or equal to y is less than or equal to 2? This one's a bit different because in this case, it's giving us f of y and it's giving us our y bounds, unlike here where we were dealing with f of x and it gave us our x bounds. So first thing I'm going to do is just briefly transition the arc length formula from x's to y's. So in this case, we'll really be using L is equal to the integral from a to b, but a to b will be along the y-axis this time. So it'll be from negative 1 to 2 along the y-axis, times the square root of 1 plus f prime of y squared dy. Now let's set that up using these equations. L is equal to the integral from negative 1 to 2 of the square root of 1 plus, and then we need to find f prime of y. So let's do that right over here. F prime of y is equal to, we'll use the power rule, negative 9y squared. So we'll say plus negative 9y squared squared dy. Now, when I plug this integral into the calculator, I'm going to put an x in place of y. The calculator does not care whether you use x or y as your variable. It really only cares about the numbers. So I'm going from negative 1 to 2, and my integrand is the square root of 1 plus, open parentheses, negative 9, and I'm just going to do x here. X squared squared dx. That matches answer choice B, 27.741. Which integral gives the length of the curve y equals 4 times the natural log of x from x equals 2 to x equals 6? Since it's asking about the length of the curve, I will be using the arc length formula here. So L is equal to the integral from a to b, in this case from 2 to 6, of the square root of 1 plus y prime or f prime squared. So if we take y over here, we're going to then try to find y prime. Y prime would be equal to 4 times the derivative of the natural log of x. Derivative of the natural log is 1 over x. So y prime is really 4 over x. That means that when we do this, we'll have 1 plus, open parentheses, 4 over x squared dx at the end. Now this doesn't match any of my choices exactly, but it looks like all I need to do is clean up this right here, the 4 over x squared. This can be rewritten as 16 over x squared. And at this point, that matches answer choice A. Now, notice that they try to trip you up here by including things like 4 times the natural log of x or 16 times the natural log squared of x, which is if you just plop of the y instead of the y prime into this second part right here. So just be really, really careful that you are using the correct arc length formula because they may try to trip you up like this on the multiple choice. The length of a curve from x equals 0 to x equals 8 is given by the integral from 0 to 8 of the square root of 1 plus 49x to the 6th dx. If the curve contains the point 1, negative 1/4, which equation could represent this curve? In this case, we're going to be kind of working in reverse. They gave us the integral with the arc length. So we know what our arc length integral really is. It's L is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. So in this case, we just have to figure out, well, what did they plug in for a and b, and what did they plug in for f prime of x? Now, we see that they have 49x to the 6th, so this must be f prime of x squared. So I'm going to say f prime of x squared is equal to 49x to the 6th. Now we can square root both sides, and we would typically want to stick a plus or minus on there. So we would say f prime of x is equal to plus or minus, and then 49x to the 6th. Well, square root of that is going to be 7x cubed. So we're looking at plus or minus 7x cubed to be f prime of x. Now, if we want to find original f of x, because original f of x is really what they're giving us over here. We have a whole bunch of y equals, which could also be written as f of x equals. So what I'm going to do is I'm going to say, if we have f prime of x is equal to, we'll go with the positive one first. We'll say 7x cubed, and I want to find original f of x. I can take the integral of 7x cubed dx. That would be 7 times x to the 4th over 4 plus c. So we would say y equals or f of x equals, either one of those works. Now I see that I have y equals 7/4 x to the 4th minus 2. So it looks like it's going to be answer choice A. So I'm going to tentatively keep answer choice A in my mind because all of these other ones, we have x to the 7th, x cubed, x to the 5th, and we know that it's going to be x to the 4th. Now, because I was able to successfully get my solution from only the positive version of f prime of x, I actually don't even need to test the negative version right there. So I'm just going to keep going with this. Now, it says that the curve contains the point 1, negative 1/4. So I can plug those points in for x and y and then solve for c. Y is negative 1/4. So we have negative 1/4 is equal to 7/4 times x to the 4th, or 1 to the 4th, plus c. So that means negative 1/4 is equal to 7/4 plus c, which would mean that c is equal to negative 8/4. Now negative 8/4 is really equal to negative 2. So then I could retake my equation over here, y equals 7/4 x to the 4th minus 2. This matches answer choice A. Let region F be the region bounded by y equals e to the x equals the natural log of 5, and y equals 1, as shown. Write, but do not evaluate an expression that gives the perimeter of region F. In previous videos, we were given similar regions like this, but then we were told to maybe find the area of the region, or find the volume if it has semicircular cross sections, or find the volume if it's rotated around a line or something. But in this case, we can actually use arc length to help us determine perimeter. Now, it's not too difficult to find the length of this and then the length of this segment, because I know that the vertical line is going to be x is equal to the natural log of 5. So this is x is equal to the natural log of 5. Now, I know that these are intersecting at 0, 1, because that's what it shows right on the graph here. And it says the line y equals 1. This is the line y equals 1. That means that this distance right here is going from x equals 0 to x equals the natural log of 5. So that distance is going to be the natural log of 5 units. Now, if we try to figure out this long distance up here, so if we have x equals the natural log of 5, and then this curve right here is y equals e to the x, we can figure out what this y coordinate is right here if we plug in the natural log of 5 for x. So if we have y is equal to e to the power of the natural log of 5, well, the e and the natural log are going to cancel there, and we just have 5. So we know that this intersection point is going to be natural log of 5, comma 5. That means that this distance right here is going from y equals 1 to y equals 5. So that distance is going to be 4. Now, the difficult distance in this case is going to be this right here. And we're going to be able to use our arc length formula to do that. So in this case, our a and b, a will be 0, b will be natural log of 5, because those are the x bounds that we are going from. So right now we're just going to be focusing on finding L, and L is this curvy distance right here. So L is equal to the integral from 0 to the natural log of 5 of, and then, well, now we have to do our square root to the rest of our arc length formula. So 1 plus, and then this is where we take y prime and square it. Now, if y is equal to e to the x, if we take y prime, well, e to the x is its own derivative. So y prime is also e to the x. So we would have 1 plus derivative of e to the x, which is e to the x squared dx. So that is the length of this curvy side right here. Now, to get the perimeter, we simply need to add all of these up. Since this is a free response question, we do not need to simplify this all the way. So I'm just going to write out my perimeter. Since it said write but do not evaluate, this is completely fine. Now notice that I also changed the e to the 2x. I changed that from e to the x squared because you can just multiply those two together. So this would be my correct integral that gives the perimeter of this entire thing. Let R be the region bounded by the graphs of f of x equals cosine of 2.4x over x squared plus 0.2 and g of x equals 2. This is going to be a multi-step free response question, and we are allowed to use the graphing calculator on this question. Whenever I have one of these where it's asking me to find area, volume, or perimeter, a good rule of thumb to use is that you're always going to want to graph out these functions if you can, so that you can see what's happening. So I'm going to graph out f of x in y1, and I'm going to graph out g of x in y2. Then I will adjust my window to make sure that I can see it properly. So I'm going to scale my x-min to be -10 and then my x-max to be 10. So we're going from -10 to +10, and same on the y, and we'll see if that is an appropriate window. Yes, it looks like this is an appropriate window, and I'm actually going to scale it in just a bit more. And this allows me to see my shape a little bit better right here. So it looks like I'm going for this region right here. Now, I am going to just briefly sketch this out so that I can draw on it, because I can't really draw on this super easily. So this is roughly what I am looking at. Now, if I'm trying to find the area of region R, and region R would be this shaded region right here, I'm going to need to do the integral of the top function minus the bottom function from this x value to this x value. Now, the problem is I don't know what those x values are, so I'm going to have to find the points of intersection. So I can do second and then hit the trace button to calculate number 5, the intersection point. Now move the little cursor over so that it's closer to this intersection point, enter, hit enter again, enter one more time, and then it's going to give us our x value. And I'm going to jot this down as the point where f of x and g of x are intersecting. And then we have one more point of intersection as well, and that's going to be this one over here. So second, calculate, number 5, we're trying to find the other point of intersection, move the cursor over, hit enter 3 times. And it is the positive value of this. So x equals 0.356988. Now I can set up my integral for area. So the area of region R, I'm going to say A is equal to the integral from this low x value to the high x value. And hang on to all of your decimals here. Do not cut it off until the end. And then we're going to have to do the top curve minus the bottom curve. Now, when they have predefined these functions for you, all you need to say is f of x minus g of x. F of x is my top curve, g of x is my bottom curve. And then when you plug it into the calculator, of course, you would need to use the actual function. So then we have our dx at the end. Now I'm going to go through and plug this into the calculator. And I get that my area is equal to 1.275 if we round to the nearest decimal right there. So A is equal to 1.275. That would be my area of region R. Now part B says region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis, which I'm going to sketch out right here. We have cross-sections that are perpendicular to the x-axis, and they are semicircles. They're going to look just like this. Find the volume of this solid. Now, I should mention as well, I have separate videos where I go over finding the volume by cross-sections and finding the area. So feel free to check those out if you need to. The new one that we're doing here is part C, but I thought it would be good to do one big review FRQ. So if we're trying to find the volume using cross-sections perpendicular to the x-axis that are semicircles, we're going to be integrating from this negative x value right up here to the positive x value over here. So V is equal to, and then when we are doing semicircular cross-sections, the coefficient that we stick on the front is pi over 8. Ultimately, the integral that we're setting up is V is equal to pi over 8 times the integral from A to B of our top curve minus bottom curve, so f of x minus g of x squared dx. That's what I'm trying to set up here. So I've got my pi over 8, and then a to b, well, we're going to use these same a to b values over here. And then we're going to take f of x minus g of x, and again, we can leave it as f of x and g of x. We don't need to write out those full functions since they have defined them for us. We're going to square that and then stick a dx on the end. Again, I'm going through this step kind of quickly, so if you want to review, I have a separate video on this topic. Then I will plug this into my calculator. And it tells me that my volume is 1.148. For part C, where we are finding the perimeter of region R, we're going to have to find what is this straight line distance and then what is the arc length here. So for our straight line distance, we can do our upper x bound minus our lower x bound. So in reality, we're just going to be doing 2 times 0.356988. So that's how I'm going to start my expression for the perimeter. And then we also need to use this arc length here. So we'll say plus, and then this is where we do our arc length integral. So integral from our low x value to our high x value. And then we take the square root of 1 plus, and then this is where we have to do our f prime of x squared. So for now, I'm just going to write it as f prime of x squared dx, and then when I stick it in the calculator, I can use the derivative function inside there. So first, I'm just going to calculate the integral right here. So I'm going to go math 9, and then from my low x value to my high x value. And then what goes in here? Well, first I do my square root, so I have square root of 1 plus, and then open parentheses. Now I need to find what is the derivative of my f of x function, which is right up here. So I'm actually going to use math 8 to do that. So math number 8, if you hit the math button down here, and then number 8, that's going to allow you to take the derivative. So we're going to take d dx of our function right here, and I'll type in that function. And we'll say x equals x because we want it at any value right there. And then we need to square that derivative. So we'll do close parentheses, square the derivative, squaring f prime of x, and then we have our dx on the end. And here's our value. So this is that integral, and then don't forget that you also need to add this. So we'll say our answer plus 2 times 0.356988. And that gets us the total perimeter of region R, 6.781. There is our completed FRQ, and this is an example of something that you might see on the BC Calculus exam, asking for area, volume, and then perimeter. If you are interested in how we got the arc length formula, I'm now going to show you the proof. Again, this is not something that you need to know on the AP exam, this is just if you're curious. So it's very similar to the process by which we get our limit definition for the Riemann sum or our limit definition of the derivative. Let's say we're trying to find the arc length from 1 to 6, from x equals 1 to x equals 6. Right here to x equals 1, I'm going to call that A, and then I'm going to call x equals 6, that's going to be B. And we're also going to consider this to be x sub 0, and then this over here will be x sub n. That means that when we're at 2, this would really be x sub 1. When we're at x equals 3, that would be x sub 2, etc., until we get to x sub n. So like we mentioned at the beginning of the video, what we're really doing here is if we first took the distance between x sub 0 and x sub n, that would be this straight line right here. That's not a very good approximation for the arc length. But if we do that twice, maybe 3 times, if we divide that into 3 equal intervals, it's going to be much better. So let's say for the sake of this one that we would do it into 5 equal intervals. An equation that we can use to find the distance of any of these little lengths is going to be our distance formula. So d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Hopefully you remember that from Algebra 1 or Algebra 2. Now in this case, we're going to say that x2, we're just going to denote that as x sub I. So that could mean any of these x values. We have x sub I minus, and then we're going to say x sub I minus 1. So that's the value that we're going to take for our change in x. And then our change in y, if we used I and I minus 1, we're going to have to do y sub I minus y sub I minus 1 squared as well. So that would be the distance between any of these 2 points. Now, the thing is, we don't want just one of these distances. We want the sum of all of these distances from I is equal to 1 to I is equal to n. So I'm going to replace this d equals with a sum here. So we have the sum all the way from I equals 1 to n. And then this is what our length is approximately. So we could say L is approximately this equation right here. Now, I'm going to change this. I'm going to synthesize this x sub I minus x sub I minus 1 into delta x sub I. And this will be delta y sub I. Now, something we can do really to any number is multiply it by 1. That's not going to change its value. And keep in mind that if we have something like 3 over 3 or x over x, those are also going to be equal to 1. What we're going to do is I'm going to multiply this second term by 1. It's not going to be 1, the number, but it's going to be delta x sub I over delta x sub I squared. And you'll see why in a moment. Right now it seems kind of weird, but you will see why shortly. Now we have delta x sub I squared over delta x sub I squared times delta y sub I squared. So what are we going to do with that? Well, what this allows us to do is I'm going to swap this with this. I'm going to bring the delta y sub I squared to the top of this and the delta x sub I squared over here. Then I'm going to factor out a delta x sub I squared from both of these terms. Now, if we have this squared and it's under a radical, that's really just like having a delta x sub I at the end. So that's how I'm going to rewrite this. Now, as we talked about earlier, we want the number of segments to move closer and closer and closer to infinity, because the more segments that we have, the more accurate our arc length approximation is going to be. So I'm going to stick a limit on the front of this. And at this point, I'm going to take away the approximately because now I have that limit on the front, and that accounts for making it the exact number. Now this delta y sub I squared over delta x sub I squared, I'm actually going to write that as delta y sub I over delta x sub I, and that entire thing is going to be squared. Now, as we move the number of segments to infinity, what is going to happen to delta y over delta x? If we think about what is delta y over delta x at just one point, that's the derivative. The slope at one point is the derivative. Now we're going to bring in some knowledge from the mean value theorem. So the mean value theorem guarantees that there is a value f prime of c sub I that is equal to our average rate of change. The mean value theorem guarantees that we have an instantaneous rate of change that is equal to our average rate of change over an interval. We're going to write the average rate of change as f of x sub I minus f of x sub I minus 1. And then that would all be over x sub I minus x sub I minus 1. And the mean value theorem makes it so that this will be true for one point C. Therefore, we can say that f prime of c sub I is equal to delta y sub I over delta x sub I. And that looks a lot like this. So now we can replace this entire thing with f prime of c sub I. That means that we have L equals the limit as n approaches infinity of the sum from I equals 1 to n of the square root of 1 plus f prime of c sub I squared times delta x sub I. Now, this is where our integration is going to come into play. Just like we did with Riemann sums, we can replace this with an integral. So we're going to replace this with the integral from a to b, and then we have the square root of 1 plus, and at this point I'm just going to write it as f prime of x, because we know that that x value is going to be there, so we have f prime of x squared, and then that delta x sub I we can just write as a dx. Now this is our arc length formula, so that is how we really get that formula. Again, it's pretty complicated. This is not something that you need to know for the AP exam, it's just something that's kind of interesting for how we actually get that formula.